it is helpful sometimes, or interesting, I guess, also to think about, well, if I've got a parametric, can I write it as a Cartesian, or what Cartesian equation does that turn out to be? And so, and then we'll look at it the other way too. Actually, in most cases, probably the other way is even easier, but let's change from a parametric set of equations to a Cartesian. And here's, all right, so we've got x equals, oh, okay. This is the first one we did. We're getting a lot of mileage on this one. X squared equals t squared minus 2t, and y equals t plus 1. So I want to change that parametric to Cartesian. Change it over to Cartesian. All right, so basic idea is easy. It's easy if one or the other of those parametric equations is an easy equation to solve for t. So I want to, first step is to pick one of the equations and be nice to yourself, make it as easy as possible. Choose one that's easy, the easiest to solve for t, which in this case y would be the easiest one to solve for t here. So I'm going to solve, in this case, the y equation, solve it for t, just because that's the easiest one to solve for t. So that's what we're going to start with. So it'd be y equals t plus 1. Subtract 1, you got y equals 1 equals t. Well, if t is equal to that, it's equal to that anywhere we go. So now I substitute that expression for t in the other equation. So in this case, I go to the x equation and substitute that for t in the other equation. So it'll be now x equals y minus 1 squared minus 2 times y minus 1. Done.
Oh, you don't have to like expand or factor.
They might do that. Yeah, let's go ahead and expand it, because I did it on my paper, so that's probably what they did. But technically we're done there. We could stop there. Yeah, just go ahead and expand it. That'd be y squared minus y minus 1 plus 1. That'd be minus 2 plus 2. Distribute there. So it's x equals y squared minus 4y plus 3. There we go. We'll stop there. Now we're done.
And you don't have to solve this roll back.
Yep.
Sweet.
Nope. Yeah, and so if you look back at the graph that we got, this makes sense if that's a Cartesian. Because if you think back to the graph that we got, I mean, we just did from here, something like this, but that's fish hook.
Yeah.
But like I said, if I extended that on out, it's a sideways parabola. That's what I've got. X is in terms of class. All right. So we can see there, so this, that not being a function of x, didn't pass the vertical line test, this is a good way to graph this one, because it's harder to graph on our usual graphing devices to graph those sideways parabolas. But here's a way. Is that okay? All right, so same thing. So find the Cartesian equation. And we're going to do x equals 4t minus 3, y equals the square root of t plus 2t. Which one does it look like would be easier to solve for t in this case?
First one.
The x, yeah. Yeah, if I solve for t here, well, I've got a mess right there, because I've got a square root of t and a t by itself. So yeah, let's solve this one. So, I mean, it doesn't matter which one you do, just make it easy, like I said, make it easier on yourself. So yeah, solve for t here, the x one. So we x plus 3 equals 4t, right? Add the 3, then divide by the 4. So x plus 3 over 4 is t. And so if I solve this one for t, then I go to the other one and substitute that in for t, the other one, so it'd be, now y equals the square root of x plus 3 over 4 plus 2 times x plus 3 over 4. Just right in for t there. This one I can say x plus 3 square root of x plus 3 over square root of 4. That would simplify. And then this one I could cancel the 2 into the 4 there. So that'd be x plus 3 over 2. So I would say square root of x plus 3, and that's square root of 4, so that'd be 2 also. Something like that. So some of them may not be anything really that you could simplify. Some of them there are. But that one we might can factor out a 1/2 if you want to do that. Something like that.
I'm guessing we're not going to do the second example we did first.
Oh, we're going to do, well, not quite that one, but one similar. The infinity?
Yeah.
No, I don't have that one on the agenda, but yeah, that would be,
A doozy?
we could probably do it. Yeah, I don't think we'll have to do quite one like that, but I do have one that has trig functions. See how that works. Okay. Yes, but let's do this one. All right. X equals e to the t plus t. Y equals e to the minus t. Same deal. Cartesian. What did it look like? Yeah. So this offers up a little more solving equation capabilities here. Test them a little bit. So I need to be able to solve one of these for t. Obviously, hopefully, you see here, y is the way to go here because we got e to the t plus t here. We don't have that over here. We got e to the minus t. But all right, so let's solve this one. Solve this one for t. And we did a little bit of this on the with differential equations, didn't we? Solve. I'm trying to solve for t here. It's e to the power, it's got a t in it. What do I do? L in both sides. One way to think of it. So we've got L and y equals, and yeah, doing that and that sort of cancel one another out and just have minus t on this side. So then it's just divide by -1. So negative ln of y equals t. Okay? And then, we can do that'd be -1 power. That's good. We'll just call that good. All right, so what do we do with that? That's what t equals. So go back to the other equation and plug that in for t. So there and there, so it'd be x equals e to the negative ln of y plus, actually minus ln of y. And again, that's a pretty good answer. We can simplify it though. And that's what I was saying. This, huh?
What they cancel?
Goes to the power.
Well, you have to be careful. You can't just cancel and make it negative y though. A couple of things we could do. Again, by the properties of logarithms, this can come inside. That's one way you can see it. And it comes inside where? Yeah, it'd be the -1 power of y. Then, now we've got the e right up against the ln. Those do cancel, so it's y to the -1 minus, which is different than minus y, because that's 1 over y. The other one I was going to show you on this, change it to Cartesian, is, one with, when you get the trig functions, it gets a little more tricky. But here's one thing. I think this is, I'm not sure they have, I gave you any of these, but it'll work, but just in case. Interesting thing about this one is, Cartesian-wise, change to Cartesian. Sometimes those identities, with trig functions, the identities come in handy a lot. It does here again. What do you know about this? Cosine squared plus sine squared equals 1. Well, if that's true, that's a equation that's true in all cases. T, no matter what t is. Well, cosine squared plus sine squared equals 1. Isn't cosine t x? This is x squared. Sine t is y. That's y squared. Ta-da. Okay. Start with that Pythagorean trig identity, and your Cartesian comes right out of that. It's a little different. And you can so what is that? Circle, radius 1, center 0, 0. The way you can get different sides, like if I had circle radius 3, I wanted in so this is kind of going the other way. If I wanted it to be radius 3, just put the 3 in front of the cosine and the sine. Yeah, because that, if I square that, that'll be 9 cosine squared t plus 9 sine squared t. And then 9 times 1 in there gives me 9. So, yeah. So that's x squared now, plus y squared. Yeah, that's x squared, that's y squared. So that's circle radius 3. Yeah. But anyway, just an interesting little thing. Yeah, if it's not cosine t and sine t, that's a little different. But I don't think there's any really. But they did want to point out there that, yeah, this is going to give me a circle radius 1, and then if you put the 3's in front, that'll give me a circle radius 3. All right, now let's go back. Hurry. Go back the other way. Cartesian to parametric. He said it's a little easier. If I've got x equals y cubed minus y, and I want to change that to parametric. Well, here I've got x in terms of a y function. Well, if you've got x in terms of a y function, what you're going to do is you're just going to say, well, let's let y be equal to the t. If x is in terms of y, let's just let y equals t. And then, if that's the case, then what about the x? Well, if y is t, can I substitute t for y? X would be t cubed minus t. Because I can just substitute for y, substitute that to be t. So that's our parametric. So the parametric equations for this, usually do the x first. So x equals tq minus t, y equals t. Which, then, on our calculators, we can't do x equals functions of y. We can do this though. So it gives us a way around that. And then if, if you got it the other way, so you got y equals x squared minus 2x minus 4, and you want parametric for that. What are you going to do there? Which one are you going to let be t there? X be t. X is t, and then y equals, well, if x is t, then that's t cubed minus 2t. Okay, that's what I was saying. These, going that way is a little easier. All right?
They work